Welcome back, everybody. So I'm going to continue going through this menu. Before, I would like to come back to the question that you asked during the break, because I think it's an important thing to mention. It's about Yarn. How far can Yarn actually optimize your query? So here's the thing. As a user of MapReduce or Spark and so on, you would like to press the button and get your results as early as possible, as fast as possible, right? So you want to optimize for latency, you want to optimize for everything. What's very important to understand is that Yarn was not designed to optimize the speed for individual users. It was designed to avoid wasting resources at the company scale. So this is meant for a cluster that you use with 100 people that connect whenever they want to the cluster, and you want to optimize the resources of the cluster to save money and resources. People often make the mistake of using Spark in production, but just triggering a single cluster just for them, and then using Spark. Of course, you can do it if you want to do research or measurements and so on, or you want to play around. But in production, that's not how you should be using Spark. You should be using it in a shared cluster with other people. Or maybe it also works on your own machine as well. But this is a misconception. And many people end up saying Spark is slow. Yes, but this is because you're making assumptions that are not met by a technology like Yarn. So I just wanted to have clarified this, that Yarn, resource management, optimizes the usage of the resources of the cluster at the company scale and not at the individual level. But it doesn't mean that you cannot get a lot from Spark. So if you really get into it and start coding the right way and so on, you can actually squeeze a lot of performance from Spark, even on your laptop. There's a lot that you can actually get from it. Okay. Let me then continue with the transformations. So we saw 3 of them: filter, map, plat map. Here's another one. It's called distinct. Distinct is basically eliminating duplicates. So if you have items in the inputs that are several times here, it's only going to output it once in the output, right? Don't pay attention to the colors. I did a little bit of a mess here. Probably even at some point I moved from a PowerPoint style to another PowerPoint style. So it just eliminates duplicates, right? So blue with blue, red with red, orange with orange, and so on and so on. Okay, that's called distinct. Just an observation for later. You probably see here that this is kind of nicely parallel-like, right? This all just goes up, down. Here, you probably see more like a spaghetti thing, right? It's a bit going in all directions and so on. I'll come back to it later, but just to give you an intuition, this here might involve shuffling, while here it might not, right? For whom is that already intuitive, that we're going to shuffle things around here? Okay, but I'll come back to this, right? But very nice that some of you already see that. So there is a distinction to be made between the kind of transformations, between the ones that are spaghetti-y and the others that are more like parallel-y. All right. Here's another one that is called sample. It's just rolling a die and saying if you keep it or if you don't keep it, right? So the parameters so first here, there's no parameters at all, right? It's just these things. At best, you might, as a parameter, provide an equality function in a language like Java and so on. Maybe you can say, okay, here's when I consider 2 items to be the same. For the sampling, you need to provide a fraction. For example, you need to say, I want a 1% sample. So if I have a million items, I only want to keep 10,000. That's a 1% sample. So you provide the fraction. And then you provide the seed. So what is a seed? Who knows what a seed is? So let me explain. It's all about what the meaning of randomness is, because here we want to pick a sample at random, rolling a die. So when you roll a die, the whole point of doing that is that you would like the results of the die to be unpredictable, right? This is when you play a board game, you want it to be random, unpredictable. But if you think of it, if you were able to know exactly the speed and the initial speed and the angle with which and the initial position of the die when you roll it, and then with a supercomputer calculate exactly where it's going to land, in theory, you could kind of determine the output, right? And of course, this is kind of no longer true in quantum physics, because then you could make the argument in quantum physics, the randomness behaves differently. And here the concept of predictability is no longer the same, right? But I'm not going to go into details. But the distinction here is between true randomness, meaning that you really cannot predict the results, or subjective randomness that in theory you could predict, but you just are not powerful enough or you don't have the resources to predict it. This is where the seed arrives. The seed is some number that is arbitrary that you provide in order to make it random. And this is where the randomness is concentrated. It's like a pill that contains randomness. Once you have the seed, everything is deterministic. So you could consider that the seed is the exact angle and speed of and position of your roll die, and then it's deterministic. So you're kind of helping the system to provide randomness. Typically, the seed is going to be taken by for the computer by looking at the time to the microsecond, and then looking at the configuration of your computer and just making up stuff that basically looks like random. And then you can go ahead. But basically what it means is that we don't know how to do perfect randomness. So we just do it in this way. This is called pseudo randomness. You simulate randomness. Another advantage of the seed is that it makes your code easier to test. Because when you have something random, you cannot write tests about it in order to see when it breaks. But if you know the seed, then you can actually test, because knowing the seed, everything is actually deterministic. Okay, parenthesis closed. This is why we have a seed also in the case of the sampling. But the most important parameter is the fraction. You want 1%. All right, and then we have a subset. So in a way, it's like the filter function, if you want, except that instead of explicitly providing a yes-no function, the yes-no is just a die roll. Okay, so these are a few, not all of them. There's many more that you can actually look up, but these are a few of the 1 RDD to 1 RDD transformation. Now there are a few more transformations that don't work on one single input RDD, they work on 2 input RDDs. Now this is new. This is something we did not have in MapReduce, but it's nothing that would be new in the relational algebra, because in the relational algebra, we do have operators that take one table, but we also saw operators that took several tables. Can you give me an example in the relational algebra of several input tables? Anybody? Or on Zoom? On Zoom, maybe? What do you have in the relational algebra that takes 2 input tables?
Join.
Yes, exactly, the join. The Cartesian product is another example. So just to give you the intuition. So this is kind of like joins, what we are going to see now. Okay. But also union, intersection, you remember, these are also things that take multiple tables. So I'll start with that and then we'll come back to the join. So the union of 2 RDDs is just the concatenation of the 2 RDDs. Now, don't be confused by the naming, because union would suggest that we're talking about sets. You do the union, intersection, subtraction of 2 sets. But one important thing to know is that the RDDs are actually, first, they allow duplicates, and second, they have an order. There is an actual order of the items. There is the first item, the second item, the 1000th item. So these are not sets of values, these are really lists of values. So when we say union, it's a bit of an abuse of language, because it's actually more like the concatenation of the two RDDs. But It's called union for some reason, and you can also implement that way the union in the relational algebra. So the union, yeah, I don't think I have more to say about that, right? Just concatenates the two RDDs. Then we have the intersection, which is more involved. So the intersection, probably see that here it's shuffling things around. So that's a spaghetti-y kind of transformation. And it's just going to build an RDD that contains items that were on both of the input RDDs. Right? And here too, you might have systems that allow you to customize the equality function, that you can tell the system, this is what equals means. This is when I consider two items to be equal. It's not trivial, this whole thing about equality, right? Because imagine you're talking about strings. Imagine that you have, I don't know, Eidgenössische, and then the same one, but instead of the umlaut over the O, you have OE, right? You would like to consider the same, right? So this is also something that in some systems you actually are able to do, to kind of allow for this kind of interpretation. Okay, but anyway, I just kept the equality implicit in there. I assume it's provided in some way. So here we have the intersection, meaning all of the items that are on both input RDDs are kept. The ones that were only on the left or only on the right are not kept. Subtract is doing the opposite. It's basically a subset of the left RDD, but we remove all of them that are somewhere on the right RDD. We only keep those that are not on the right. So this is why it's called the subtraction. It's the same that you have in the relational algebra, right? So black and purple here are kept because there's no black and, well, they're supposed to be, if I had done my slide properly, there's not supposed to be black and purple on the right. And the orange is not output because it is on the right RDD, right? So this is called subtract. Okay. Then the Cartesian product of two RDDs. So here I needed to draw them differently. Instead of having the two at the top, I had one on the left and one on the top. So a Cartesian product of two RDD is creating actually an RDD of pairs. It's an RDD of pairs, and each pair has the left part of the pair is one item from the first RDD, and the right part of the pair is an item from the right RDD, right? And I'm just outputting this huge RDD of pairs out of the two input RDDs. Now, be careful, because that's like in relational database if you do the Cartesian product of two tables. I let you imagine if you have a billion items on the top RDD and a billion items on the other one as well, and you do the Cartesian product of that, you're looking at 10 to the power of, so it's 9 plus 9, 18, 10 to the power of 18. That means you're looking at a quintillion items. This is going to crash your cluster. And in fact, this is so dangerous that many systems, many implementations of Spark by default prevent you from computing Cartesian product. If you try, you will get an error, and you can bypass the system on the command line by saying, activate Cartesian product, that of course at your own risks, right? So you can activate Cartesian product, only do that if you know exactly what you are doing, because otherwise the cluster is going to crash. Okay. All right, so that's the Cartesian product. Why not join? Because we need keys for that. And I'm not talking yet about key values in the input RDD. So the join is coming back a bit later, right? Okay, any questions so far? Right. So we are just going to the menu, right? Filter, map, flat map, distinct, Cartesian product, union, sample, intersect, subtract. And that's not even all of it. There's many, many, many more, right, that you can actually look up. But these are the most popular ones. All right, these were all transformations, meaning that if you only do transformations, nothing is going to happen or be computed. You need the actions in order to trigger the actual computation. So let's look at the actions. A first action that you can do is collect. Logically, collect is just the identity function. Just takes a collection of items, returns the same collection of items. But the difference is physical. The input of that is an RDD of item, meaning that's something distributed over the cluster, right? You have all of your items all over the place in the cluster. Collect triggers a download a download of all the items from the cluster to your machine. So every item is going to be downloaded to your machine to a list, but an actual local list in your memory, like a Java list, a Python list, locally. So a consequence of that is that if you have an RDD with 1 billion or 1 trillion items, it's not a good idea to call collect. But if you know, because of the way you design your query, that the RDD you're looking at after applying 10 transformations has a small number of items, then you can collect it. And then you have a local list on your machine in Java or in Python. And once you have your local list, you can go ahead and do things with it using Python or Java that are no longer going to involve Spark. Okay? Who is clear on what collect does? Right. Very popular in convenience, collect. But again, be careful, be aware that you're going to crash the whole thing if it contains 1 billion items. There is count. This one is safe. It's going to compute the total number of items in your collection. And that also works if there's 1 trillion items. It's just going to distribute the count somehow over the cluster. Every machine will count, and then you add all the counts. Right? So this is count. We have count by value. That is in the case that your collection of items might have duplicates, then it counts how many duplicates there are of every value. So in that case, we might say, okay, there are 12 blue items, 4 red items, and 6 green items. I don't guarantee correctness. It might be I miscounted or something, but just to give you an example, right? So this is count by value. And this is an action. Again, that means that this 1246, it's not an RDD 1246. It's really something local. It's a Python dict, if you want. It's a Python dictionary, a map that says blue 12, red 4, green 6, but it's local to your computer. Okay. Then we have take. Now, take is very convenient if you cannot use collect because there are too many items. So if you cannot use collect in that way, then just pick the top 10, right? The top 10, the top 100. And this is something you can do with take. Take is going to return the first n items, in that case, the first 4. So take takes an argument, which is a number of items that you want. All right, take is safe. This you can actually do even with large collections. That would be in SQL. What would it correspond to in relational algebra in SQL? Take. Anybody? On Zoom? What is the SQL equivalent of that?
Limit.
Yes, correct. This is the equivalent of limit in SQL. So you could implement limit as a take action in Spark. Very good. Then we have top, which is the opposite. It's the last ones. Why is it called top? I have absolutely no idea, but it probably means that somehow you view the RDD as what computer scientists call a stack. You know, a stack is when you pile up things in this way. That's called the stack. There's the top of the stack, then you can pop or you can push, and this is called the stack. And somehow that comes from this notion of pushing, popping. And so the top of the stack, if you consider that the last ones would be the top of the stack, this is why it's called that way. But anyway, you could also have called it last, right? Basically the last 4 of the RDD. Okay, so they are almost the same, but it's just that it's the order here is important. You also have take sample if you want to just roll a die on which ones you take. But again, that's not the same thing as sample because sample outputs an RDD. Take sample doesn't output an RDD. It outputs a local list in your Python, in your notebook, on your machine that you can process locally. Okay. Reduce. Oh, here we start seeing the reduce coming back. What does it do? Well, it's not actually the reduce of MapReduce, something different, but it's the idea that you want to aggregate something. For example, you have plenty of numbers, you have an RDD of 1 billion numbers and you want their sum, or you want their average, or you want the max, the mean, any aggregation. Then you just say what you want. You say, okay, I want to use plus. You need a binary operator, and Spark is going to apply as all the way to the entire RDD, one by one, this operator. There is the assumption, though, that this operator is commutative and associative for things to work. These are exactly the same assumptions that we had to use the reduce function as the combine function, if you remember. So you can do this if it's associative and commutative. Why do we require associative commutative? Because there are no guarantees of in what order the plus is going to be applied over there, because it's all distributed on your cluster. So it's a bit of a mess and you have no guarantee on the order. But if it's associative and commutative, you don't care about the exact way that this is computing. So this is called reduce, and you get a single value back to your machine. Okay. There are a few, maybe I should add a slide for them, but there are other actions that are useful. One of the useful actions is write. You ask Spark to write back to HDFS or to S3 or to Azure Blob Storage. That's also an action. Then it's not going to download anything or put it on your screen. It's just going to write it back as a directory containing 1,000 files, shards to HDFS. Okay, so these are the actions. This is what you can do. And when you trigger the action, then the computation starts being executed in the cluster. Who is following? Okay, very good. And by the way, this is very practical. You are going to have exercises doing that. And in fact, you're also going to have this as a practical exercise on the exam day. So I recommend looking into PySpark and making yourself familiar with that. On the exam day, we'll give you a data set. And we will ask you to write PySpark in order to answer questions. Right, like a data set of movies or a data set of the TAs have a lot of imagination in what they find. And we'll provide you the data set before the exam. We usually like to do that to reduce your stress. And so writing in PySpark, using PySpark to query the data set is on the exam. The other thing will be PostgreSQL. You will also have PostgreSQL at the exam, writing SQL. And the other two programming assignments, we have not covered them yet, so I'll talk about them later. But now you already have two. It's PostgreSQL, writing SQL, and it's PySpark, which is basically what we are doing right now. So I recommend to really put care into solving the exercises and making sure that you know PySpark. Okay, it's all going to be in a Jupyter notebook. Right? Okay. Now, moving on. I repeat, I already said it. In MapReduce, we look at collections of key-value pairs. In Spark, we don't restrict ourselves to key-value pairs. It can be anything. Collections of items. An item may or may not be a key-value pair. It doesn't need to be. So a particular kind of RDD is a pair RDD, meaning that the item is a pair. And it turns out that Spark has its own restaurant menu as well, for the special case that the RDD is actually an RDD of pairs. For example, you have a transformation called keys that takes an RDD of pairs and returns the RDD with just the keys. You drop the values. It only works if this is actually an RDD of pairs, right? If this is not an RDD of pairs, you cannot do that. But if it is, then you can. So keys does that, and of course values, right? That's just the other one. So you can extract the keys and the values. Another one is reduce by key, meaning that you group together the key value pairs that have the same key, and then you reduce by calling plus or count or max or min or whatever on the values. Now, this is the MapReduce reduce. So the MapReduce map is flat map, and the equivalent of the MapReduce reduce is reduce by key, because this is exactly what MapReduce is actually doing in the reduce part. Who understands that? So flat map, reduce by key. So now we basically established that Spark is officially a superset of MapReduce because we can emulate MapReduce with Spark. We can do what MapReduce does with Spark, but we can do much more than that. So now MapReduce is just a special case of Spark. Now we have group by key. So group by key is if you don't want to use plus or whatever, and you don't want to aggregate the values that have the same key, but you want to keep them all as an array, for example. So in that case, you just group by key, but then all of the values that had the same key, you just keep them all as a list. right? This is called group by key. Sort by key is just outputting the same RDD, except that now everything is sorted by key. I think that I pushed the geekiness here by actually sorting them by wavelength here, but not that it matters, but this is the idea, right? You basically sort them, if it's integers, by ascending integer and so on. And if it's string, then alphabetical order, right? So sort by key. Here you might need to supply the function that says less than, right? Because that might depend on what you're looking at. If it's strings or dates or integers, it's obvious, but if it's something more exotic, then maybe you need to tell Spark how you compare two keys. Okay, another one is map values. So you supply a function that maps an item to another item, value to a value, but Spark is only going to apply that function to the values, not to the keys. So the keys here are exactly the same ones. You keep exactly the same keys, but the values are transformed. Okay, so this is called map values. Now we have the join. The join is back. So why did I not talk about it earlier? Because the join only makes sense if you have the notion of key value. So now we have two pair RDDs, have key values on both sides. And what join is doing is that it's looking at all combination of key values from each side that have the same key, right? So whenever it finds two key values with the same key, then it outputs some sort of triplet with the key and then the value from the left and the value from the right. Actually, it's not a triplet, it's still a key value, right? It's just that the key is the key and the value is just a nested pair of the two values, right? Okay, so this is the join, and this is also how you would implement the relational algebra join. If you consider that in the key, you would have all of the primary key from your relational table, all the columns in the primary key, then in the value, the other ones. This is the join. We also have subtract by key. So you see there's such a huge menu to pick from with plenty of exotic functions. So probably this one is used less often, but you basically output a subset of the left pair RDD and you remove all of the key values when the key appears on the right. So this is subtract by key. Count by key is telling you for every key how many times it appears. This is an action. You saw this is no longer a transformation, it's an action. And this is telling you how many key values you have for each key. It's very similar to count by value, but this one works on key value pairs. That's the difference. Okay. Note that count by key would be identical to first calling keys followed by count by value. It's just identical to do it that way. So you can take it as a shortcut. Lookup, what does lookup do? Well, you have a pair RDD, you supply a key and it gives you the value or the values that are associated with that key, right? So if I say orange, there's one in the middle that's the orange key and I get the black value. Okay. That's it, we went through the restaurant menu with all of these actions, these transformations, and so on. And so now you probably understand by now that it's like a Lego game. So everything is modular. You can have data wherever you want. Can be in S3, can be in HDFS, can be on your local hard drive, can be created on the fly in memory. Can be any format you want. Maybe it's just text. Maybe it's a JSON lines data set. Maybe it's Parquet. Maybe it's some XML stored on HBase. Doesn't matter. Everything we've seen in the first part of the lecture. And then you can feed that into Spark. And then you can write in PySpark, for example, functions to transform and transform and transform and transform. And then you can output this on your screen in your Jupyter notebook, locally on your drive, back to HDFS, back to S3, back to Azure Blob Storage. So you see now you have everything. You have the whole Lego game and you can go ahead and query your data sets. And now I hope that you see how everything that we've been doing from the beginning of the semester, it's not disconnected, it's all connected, it's all complementary. Now you can just pick anything you want, any format, any location, any technology. You can use MapReduce, you can use Apache Spark, you can use also some others we will see later, right? Okay, so now this is a huge milestone. for the lecture, because now you have knowledge that you can actually start querying your data set for your bachelor's thesis, master's thesis, PhD thesis. Now you have the whole, already a complete set of tools. Any questions so far? No questions on Zoom? Are there any questions on Zoom? No questions either? Okay. So I have 15 minutes left. Now I'm going to do the same thing I've been doing every week since the beginning. I'm going to go to the physical part. So every week almost, I first presented to you the abstraction level, the logical part, and then how it's actually physically implemented, the architecture. So now I'm going to do the same, because now I didn't tell you anything about how internally Spark actually does all of that. So let's look at the internals of Spark, and you will see what we did with MapReduce and with HDFS will actually be useful here, because there will be some deja vu in here. Okay. Let's come back to the remark that I made earlier, that some of the transformations or actions were spaghetti-y and some others are not spaghetti-y. So let's start with those that are not spaghetti-y, meaning the ones that basically have this verticalness in the way that this is done. Why is that important? It's important because if you consider computing this, for example, you need to compute this item right there. What part of the input do you need to compute it? All you need is this item right there. You don't need this, you don't need this. So it's kind of local. There is some locality in that, right? And when you have a transformation that is not spaghetti-y, you can in fact cut it like this into a partition of transformations, and these are actually tasks. So you have task 1, task 2, task 3, task 4. Task 1 is going to map the first 3, task 2 is going to map the next 3, task 2, task 3, the next 3, and task 4, the 2 remaining items. Who's following? This is in fact what we've seen in MapReduce, right? Both for the map phase and for the reduce phase. This is exactly how this is done, right? So this is parallelized in this way. And I'm going to get more precise on what I mean with parallelize. Okay, so now we have made 4 tasks in order to physically compute the transformation. It's physical, right? The user doesn't care. The user of Spark just sees this, right? This is a physical implementation. Okay. By default, it's not very different from MapReduce. By default, Spark is going to try to size the tasks in such a way that roughly the input is 1 HDFS block, roughly. So 128 megabytes. I'm saying roughly because, again, we have this problem I mentioned earlier, is that if you do it strictly, then you might cut a key value or an item in the middle, right? You don't want to do that. So the correspondence between the MapReduce splits and the blocks is not perfect. So the last record in a block might actually end in another block, right? So this is roughly. So roughly 1 task per HDFS block if it's your first transformation. Okay. So now I depicted the physical and the logical layer, and if I can, for the lecture, will remove the toolbar at the bottom, is going to be probably easier. There you go. So on the top, you have the logical level, where you have a logical transformation that takes an RDD, outputs another RDD. So RDD1 map to RDD2. That might be a map, a flat map, a filter. And now you have the physical layer, where I'm showing 4 machines in the cluster. Could be 1,000, right? But I just put 4 in there. And each machine executes 1 task, right? So machine 1 executes task 1, the first 3. Machine 2 executes task 2, and so on. So that would be the case that I have 4 HDFS blocks that gave me 4 tasks. Of course, the number I exaggerated. If you have 128 megabytes, you're not going to have just 3 items. It's more likely like you have 10,000 items or 100,000 items, right? So this is all oversimplified here. So 4 HDFS blocks, 4 tasks, and I compute the tasks, 1 task per machine. Okay. Now, and again, that should not be new to you because we've done that with MapReduce already. If I have 4 HDFS blocks giving me 4 tasks, and I execute it on 4 machines, then I potentially have a problem. Because what happens if a machine is faster than the others, or there is a task that is much smaller than the others, then one machine is going to finish before everybody else. Another machine might take forever, and all other machines are waiting for it. So this is not very efficient. So in practice, you don't want to have as many tasks as machines. I'm using the word machine. I'm going to use the word slot again later because that's more precise to say slots. But anyway, let's say machine for now. So now I have an example with 11 tasks, but I'm not taking 11 machines. Instead, I'm only taking 4 machines, and I'm spreading these 11 tasks on 4 machines. And you see, maybe the 4th machine is so fast that it manages to compute 4 tasks, and the 1st and 3rd machines are a bit slower, so that they have less tasks. This is done dynamically. It's like the postcards last time. It's like when you start the whole system, they get task 1, task 2, task 3, task 4, and then they get the next task when they are done. So whenever a machine is done, it asks for another task, and it's getting another task as long as there are tasks, and at the end, there's no more tasks anymore, and then they start idly waiting, okay? So we spread tasks over executors. Executor is just the fancy name in Spark for a slot. Sorry, for a machine for now. I will get more precise in the next slide. So we have executor 1, executor 2, executor 3, executor 4, and we dynamically assign the tasks. Who follows me? Okay. So executor is a new term. It's the terminology in Spark. Okay. Technically, executor is a yarn container. That's going to be a yarn container. Okay, now this is why I was saying that slot, executor, machine, so it was a bit fuzzy, but now I'm going to be more precise. So an executor physically is actually a yarn container, meaning that it can have 1 or more CPU cores and it can have a certain amount of memory. So let's imagine, for example, that executor 1 has 2 cores and it has maybe 10 gigabytes of memory, and executor 2 has 2 cores and also 10 gigabytes of memory, right? If I have 2 cores, then I can do things in parallel. I have 2 slots. Every CPU core gives you 1 slot. It's like the MapReduce slots. So it means that on core 1, I can take care of 2 tasks, and in parallel at the same time, on core 2, I can take care of 3 tasks. And executor 2 is going to take care of 2 tasks on its first core and of 4 tasks on its second core, right? So you see that now we have several levels. We have the CPU cores, 1 slot each. Then we have the executors. It's sharing memory across cores. And then we have the machines, because a machine might have several executors. You remember in Yarn, a machine can have several containers. Okay. So this is how it works on the physical level with how I assign the tasks to the physical resources. And every CPU core is sequentially taking care of tasks, one after the other, but across the cores and across the machines is going to be in parallel on your cluster. Do things add up now? A lot of that should not be new to you because that's similar to MapReduce. This idea of sequentially calling the function within a task and this idea of sequentially taking care of tasks within the same slot, this is not new. We saw it. What's new here is the idea that the cores share memory and that you have executors that might contain multiple cores. Now, this is new. Okay. Okay, let's continue then. What if I don't have a single transformation, but several? Because again, this is not MapReduce anymore. In MapReduce, we didn't have that. It was just map, shuffle, and reduce. But in Spark, you might have a sequence of transformations. Transformation 1, then transformation 2, then transformation 3. So imagine that I'm sticking for now to these non-spaghetti transformations, just transformations that are parallelizable. So now if I naively proceed with what we've just seen now, that basically we can just divide like this on machines in parallel and so on, naively, I could come up with something like this, right? You apply the first transformation, then you just shuffle things around, then get on another set of machines, apply the second transformation, then you shuffle around, then the third one. Do we need to shuffle here? Who thinks we do need to shuffle? Who thinks we don't? We don't, right? Why would we shuffle? It's just so much non-spaghetti that we can do things in parallel like that. So in fact, we don't even need to change the machines. We can directly go ahead and execute. Maybe it's a map, then a filter, then a flat map, and we can just do it on the same machines. So on the first machine, I have one AGFS block, and I apply 3 transformations only on that AGFS block. And then I do the same on second machine, third machine, and fourth machine. So in fact, if I have several transformations that are non-spaghetti, it's called a narrow dependency, then I can just execute them very efficiently on the same machines. This is called a stage when I can do something like that, right? So a stage is a sequence of transformations that are non-spaghetti and do not require any shuffling. And it means that physically, I don't even have any boundary between the transformations anymore. I just do it in the same slot, in the same machines. Right. This is called a narrow dependency, right? That's basically just the formal way of saying non-spaghetti, the narrow dependency. So it stays on the same machine. It is the same stage. So now I'm redrawing. So this was the one transformation case, one single transformation. So now I just redid the same slide now, considering that in that case, I have 2 transformations. The 2 transformations are non-spaghetti, narrow dependencies, filter, map, flat map. So what happens is that I can just do them in one go. I only have, for example, for the first block, I have only one task, even though it's several transformations. For whom is that clear? Okay. So what happens is that on the logical level, I have a map followed by a filter. On the physical level, I have my AGFS blocks, and within one slot, within one task, I take the first item and I call map and I call filter. So it might or might not be there, right? So map filter. Then I take the second item, map filter. Third item, map filter. I'm done with task 1. Then I take another item in task 5, map filter, map filter, map filter. Done with task 5. And while this slot was taking care sequentially of calling map and filter on every item, every other slot was doing the same thing with different tasks. It is equivalent, logically, to having done first mapping and then filtering. It's just more efficient. It's more efficient because we don't shuffle data around, we just keep it where it is. So in fact, the intermediate data between the map and the filter doesn't even exist anywhere. It's kind of in the air while being computed, but we never actually store this intermediate RDD between the map and the filter, right? Who is following? Okay, this is almost, no, this is 10. So I'm going to end here, and we'll continue next week with data frames, with Spark SQL, and with how we do the shuffling on that. But hopefully it should be clear enough. Hopefully you made a connection to what we've seen last week with MapReduce and with the previous lectures. And if you have questions, you can ask them on the Element server. You can write us emails, do the exercises. Again, there will be practical programming assignments with PySpark at the exam. So thank you very much, everybody, for coming. Enjoy the exercises. And I'll see you next week, as usual, at 8 a.m. Thank you, Wenxi, for moderating. Thank you, everybody.